Hello there. We are studying the Newton codes formulae. There are two types, closed and open. And we have also observed that they are not suitable for long uh, computing because there are many errors. As we have seen, when you approximate a function by a high degree polynomial, then the error can be very huge. Not just that, if you change the x value slightly, there can be large perturbations. The perturbations can be very bad in the polynomial values because the degree of the polynomials are very large. So what we have found out is that instead of approximating the function by a single polynomial, you can cut the whole interval into some smaller subintervals and then apply the smaller degree interpolation to these subintervals. So this is what we are going to do for the integration formulae also. And let me start sharing my slides. I do hope that you have now started seeing them. So this is what leads us to the composite numerical integration. So these are normally unsuitable, the Newton codes formulae, whether you are taking the open ones or the closed ones. And the high degree polynomials will be required if you're looking at large intervals, cutting the large intervals into several subintervals and then taking many nodes and interpolating with a high degree polynomial. So what we are going to do is to do a piecewise approach to these low order Newton codes formulae. We start with an example to say how effective this piecewise approach can be. So when we integrate the function e power x dx from 0 to 4, that is simply e power 4 minus e power 0, because the integration of e power x is e power x. And you are looking at definite integration, so the constant term doesn't come, and this is the answer, 53.5981500331. Now suppose we use the Simpson's one-third rule. We have seen that instead of looking at the trapezoidal rule, Simpson's rule is more effective. So this is the best rule that we have among the rules which are obtained by using a single polynomial. So use Simpson's one-third rule and we get the formula to be 2 by 3, because now h by 2 is 2 and then one-third is given by Simpson's one-third rule, and you have e power 0 plus 4 e square plus e power 4, and this answer turns out to be 56.76. So that is almost an error of 3, which is rather unacceptable. Meaning out of 50 you are giving the error to be 3, and it's supposed to be the best rule, and our interval is also not very large. It's just the interval of length 4, and that therefore this error is rather unacceptable. What we then do is that we cut the interval 0 to 4 into two parts, 0 to 2 and 2 to 4, and then we apply the Simpson's rules to both these intervals. So you would have 0 to 2 e power x dx and 2 to 4 e power x dx, and these are the function values. Now the h is 2, and so h by 2 is 1. So we have 1/3 e power 0 plus 4e plus e square. That's for integration from 0 to 2. And the integration from 2 to 4 will give you 1/3 e square plus 4e cube plus e power 4. And this answer, if you compute, is much closer to the actual answer, 53.86 instead of 53.59. You are getting the answer to be much closer. Definitely closer than applying Simpson's one-third rule on the whole interval 0 to 4. Okay, and now let's try to go one step further. We apply the Simpson's one-third rule to the subintervals of length 1. So we will have them to be 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Now let's apply the rule to all these 4 intervals separately. Now h is 1, and so h by 2 is going to be 1 by 2. And the one-third rule will give you 1 by 3. So you get 1 by 6 as the constant, which you multiply to the formula. And you have those terms coming in, and if you compute the answer, this is now much better. Even the Simpson's rule applied to 2 subintervals. So it's very common and very natural to expect that the error will decrease as you apply Simpson's one-third rule to smaller and smaller subintervals. But the problem then is that you will have to do more computations. So we will have to strike a balance. We will have to strike a balance on seeing where we apply the which formula we choose, how many intervals do we have, and this is why the error will be more important. So let's see. We will go ahead and see how the error is described. So to generalize this procedure, we will have an even integer. We will divide our interval AB into n subintervals. These are the even number of subintervals, and apply the Simpson's rule to the pair of subintervals. Okay, so this is what happens. You start with x0, which is here, and your b is xn, and x0 to x2. This is the first pair of subintervals to which we apply Simpson's one-third rule. The darkened blue part that we see here, this is a typical part that is going to be considered for applying Simpson's one-third rule. It starts from x2j minus 2 and goes up to x2j. And then we apply the Simpson's one-third rule. So we are going to interpolate our function by a degree 2 polynomial over these three nodes. And then we take the corresponding integration formula. So here we see that the blue line is the y equal to fx. The red, the black piecewise quadrics, those are given, and then you are taking the area bound by them. So this is the piecewise, or what is also called composite, Simpson's one-third rule. So the general case is as follows. You will have h equal to b minus a by n. Xj is going to be a plus jh for 0 going from j going from 0 to n. And the formula then reads, your integral a to b fx dx is summation j going from 1 to n by 2 x 2j minus 2 to x 2j. So you have x0, x1, x2 up to xn. We are going to look at x0 to x2, then x2 to x4, then x4 to x6, and so on. So this is how we are going to look at them. And this particular integration is summation j from 1 to n by 2, and the Simpson's one-third rule applied to each of these subintervals will give you h by 3. Then there are the three function values inside where the endpoints will not come with coefficient. The corresponding coefficient is 1, whereas the middle point will have 4 as the coefficient, minus h power 5 upon 90, the fourth derivative at xi j. Okay, so this is the error for the Simpson's one-third rule applied to each of the subintervals. This xi j is between x2j minus 2 to x2j as we would have it natural. We simplify this formula. This is a long formula, and we are going to simplify. H is anyway going to be common, so we can pull h out. You will also have several parts appearing inside with same coefficients. So there is this 4 f of x2j minus 1. So these odd ones, the odd numbered nodes, are going to come with multiplicity 4. Their coefficient is 4. For the even ones, the very first one will have coefficient 1, the end one will have coefficient 1. But the other one, so for instance, f of x2 has to come with multiplicity 1 for the interval x0 to x2 and also for the interval x2 to x4. So it will come with multiplicity 2 in the final formula. So we are going to look at all those which will come with the same coefficients and collect them together to write down the final formula. Moreover, for the xi j, where we are going to apply the fourth derivative of the function, for that we can use some mean value theorem, but that will knock off a 1h. But anyway, so we will have a single mu. Instead of having several xi j's, we are going to get a single mu in the error. And so the final statement reads as follows, that you have a function which is 4 times continuously differentiable on AB. N is even, h is b minus a upon n, and xj are defined accordingly. There is a mu in open AB for which the composite Simpson's rule for n subintervals is, with its error term, integral a to b fx dx equal to, this is the formula, which is h by 3, which is the common part for all of them. FA and FB, as we see, are coming with multiplicity 1. F of x2j, all the remaining ones, which is like j equal to 1 to n by 2 minus 1. So they are all going to come with multiplicity 2, and all the remaining nodes, which are the odd numbered nodes, they are coming with multiplicity 4. And then there is an error term, which is b minus a upon 180 into h power 4, the fourth derivative of the function applied to mu. This is the nice and simple formula for the composite Simpson's 1/3 rule applied to the interval AB. The function has to be 4 times differentiable. Now the error term, as I told you, when you apply the mean value theorem, instead of getting the xij's, we are going to get a single mu, but that reduces one particular h. That reduces the power of h by 1. But this is, and in the original one, it was h power 5 when you were using the standard Simpson's rule. But this is not something that you should really worry about, because the standard Simpson's rule will have a fixed h. It will just depend on the number, the nodes that you have, whereas here we have a flexibility using n. We can have smaller and smaller intervals for the composite ones, and therefore h can be made smaller. The earlier one was simply h equal to b minus a by 2. You are using Simpson's 1/3 rule, so you should take 3 nodes, x0, x1, x2, and therefore your h was simply b minus a by 2. But here you can reduce h, you can make h smaller and smaller, and therefore the h power 4 vis-a-vis h power 5 in the earlier rule doesn't seem like a bad bargain. Okay, so we similarly have composite trapezoidal rule, meaning of course the Simpson's rule was obtained after trapezoidal rule. Then we went to composite Simpson's rule, so there are similar composite trapezoidal rules. Here we need the function to be only twice differentiable. H is b minus a upon n, xj is defined accordingly, and we have a similar formula for the with the error term, which says that there is a mu, with which the formula looks as follows. So once again we have the FA coming with multiplicity 1, FB coming with multiplicity 1, and all other f of xj are coming with multiplicity 2, because they will be added up when you are going to take the middle ones, which will come for the trapezoidal rule for both the intervals on the two sides of those nodes. The error is b by a upon 12 h square double derivative of the function upon mu evaluated at mu. So this is how the error is described. Let's see how the picture looks like. So typical interval is given here in the dark blue color. We see that it's going from xj minus 1 to xj. You are simply drawing this vertical, horizontal, the slanted line, joining those 2 points on the graph, and then you have the trapezoid and you are taking the area of the trapezoid. This is the formula that we have for the composite trapezoidal rule. This is the closed Newton-Cotes formula. The open Newton-Cotes formula gives us the midpoint rule, and that is written in the following language. Here we are going to need that n is even, because you are going to take the midpoint, right? And then you will have x minus 1 and x n plus 1. So those are the special things that we have to consider here. There is again a mu, for which the composite midpoint rule for these n plus 2 subintervals with its error term is as follows. As simple as it is: 2 times h summation j going from 0 to n by 2 f of x2j, and the error is b minus a upon 6 h square f double derivative at mu. And the picture would be as follows. It's an open Newton-Cotes formula, so you will ignore x minus 1, you will take x naught, then you will take x2, x4. A typical one which is given here again in the dark blue color is for x2j, and you are drawing that particular rectangle and taking the area of this rectangle. So these are how the composite rules given. Let's do an example for these and compare the various composite rules. So suppose we compute this integral 0 to pi. sin x dx using the above methods, and we want the error to be less than 0.00002. So we have this requirement on the error, and we are going to define our h accordingly. So that's what we will have to do. The error in the composite trapezoidal rule is given by this formula, pi h square upon 12 f double prime at mu, which is pi h square upon 12, and if you put mod to this, the function fx is sin x, the double derivative is minus sin x, but you are putting mod, so it will simply be mod of sin mu. And then the condition on the error, our requirement is that this error has to be less than 0.00002. So that tells you that pi h square upon 12 mod sin mu, which is already less than or equal to pi h square by 12, because mod sin is less equal 1. This is less than 0.002. So you can now do simply, you can multiply by 12 to the error, divide by pi, and take square root, which will give you that h has to be less than 0.00874038744. This is the h, and that will tell you that the number of sub-intervals that you have to take. Remember, we are looking at the trapezoidal rule. Okay, so the number of sub-intervals have to be bigger than or equal to 360. So we are only going from 0 to pi, and between them we have to take 360 intervals to apply the composite trapezoidal rule and compute the approximation to our integral such that the error is less than 0.00002. Imagine the number of calculations that we will have to do if you are taking 360 sub-intervals. Instead, if you apply the composite Simpson's rule, then the error is fourth derivative, which is again, our function was sin x, fourth derivative is again sin x, and you are putting a mod. So the condition of required accuracy will tell you that pi h power 4 is less than 0.00002. The difference between Simpson's rule and trapezoidal rule is that, first of all, for trapezoidal rule it's only h square and you are dividing only by 12, whereas here it is h power 4 and you are dividing by 180. So those are the two big plus points when you are looking at Simpson's rule. So this says that h has to be less than 0.18, 39, 87, 43, 167. Effectively, it should be less than 0.18. And therefore, it says that n has to be bigger equal 18. Very small. Okay. And what we then get is that the composite Simpson's rule gives the required accuracy for a smaller number of subintervals, of course. You have n equal to 18, and out of them you are going to take pairs and apply the composite Simpson's rule to them. So just because you are applying the quadratic instead of looking at just the straight line, you are getting a much better accuracy. The comparison of these two rules, the composite Simpson's rule and composite trapezoidal rule, there are, of course, if you are looking at the same n, then you are going to have the same number of calculations in both the rules. For instance, if you were looking at the composite Simpson's rule with 18 calculations, this is what we are going to get. And our answer is actually equal to 2. So you would have that this is 2.0000104. So it's giving you an error of less than 0.00002. Remember, look at this, that here you have in the summation 8 values, here you have 9 values, and the addition and so on. So you have 17 or 18 calculations. Whereas in the trapezoidal rule with the same number of steps, you have the same number of computations. There are 17 values, forget the sin 0, sin pi. There are exactly 17 values, but the answer is very different. So the error that you are going to get for composite trapezoidal rule is slightly worse than the error which is coming for the composite Simpson's rule. So these are the errors which are there for the truncation, which are called the truncation errors, because they are coming from the errors given by the interpolands, the interpolating polynomials. So we will still have to discussed the round of errors, and we have already seen that numerical differentiation was an unstable method. It was an unstable method. What about numerical integration? Is it unstable or stable? We will see that in our next lecture. So stay on. We will continue discussing these interesting mathematics and be looking forward to this. Thank you.